Okay, hello everyone. Let me open here. Good morning. My name is Furkan Boyraz, and I'm the senior software engineer in Avalabs and Ava Cloud. Today I will try my best to explain you the encrypted ERC protocol, which enables confidential token transfers. So as you all probably heard it maybe at least once, the mission of Avalanche is to digitize all the world's assets, and this is through the tokenization. But when you think especially from an institutional perspective, you have this barrier of lack of privacy. Actually, you can think this as a consortium of chain, like a bank chain with multiple validators, each operated by different institutions. Each bank needs to hide their own user data from each other while maintaining verifiability. So this is why we created the eERC protocol. So eERC essentially enables confidential token transfers while ensuring compliance. So when we mean confidential here, it means that it hides the numerical values. As you can see from this small diagram, the sender and receiver, their addresses are open to public, so anyone can see who is making these transactions, who is the sender and the receiver. But the balances and the amounts in the transactions will be encrypted. So this is what we call confidentiality. If the participant identity, so the addresses in the blockchain case, if they were hidden, then we would call this anonymity. When we mean ensuring compliance, we mean there is a auditor key as well, the baked into the protocol that the deployer of the protocol can set and change later. This key essentially enables us to have compliant transfers while having confidentiality. So we leverage ZK Snark's Growth 16 and partially homomorphic encryption, and the whole system operates fully on-chain. So as I said, the key features are the confidential transactions, the balances and transaction amounts are hidden from third parties. Every operation, like proof generation, encryption, and decryption, they're all happening on the client side. There is no off-chain actors like relayers or stuff like that. So it's, again, fully on-chain. It's just a set of smart contracts that you need to deploy and some front-end SDK that you need to integrate to your the app's front-end. It has dual mode operation. So this, essentially, we have two modes for eERC. One is standalone, the other one is converter. Standalone means that when you deploy a new eERC contract, you can set it to be a new ERC-20 as well. So you're deploying a brand new token, but it will be private from the get-go. This gives you better privacy benefits because in the converter mode, by the way, it enables you to basically convert the existing ERC-20 tokens to their corresponding encrypted versions. But during this operation, you obviously need to deposit some existing public tokens to the protocol, which everyone can see how much you deposit. But when you have the standalone version, it gives you this better privacy benefits because the total supply of the token will be encrypted from the beginning, and you have private mint and burn operations as well. And the protocol is chain agnostic. Essentially, the logic is chain agnostic because it's very efficient. But right now, we have full EVM compatibility. So what makes eERC unique and practical compared to previous protocols? I want to start with the large values. So it can efficiently enable users to encrypt and decrypt very large numbers. And it's very efficient. The security, by here I mean it prevents front running, but this is not the front running that we are used to in DeFi, in Uniswap or something. I will talk about this in a bit. It has the built-in compliance, as I said, and it supports encrypted metadata along with the transactions. So now, how do we handle large values? So actually, I want you to kind of visualize this on your mind. Normally, when we are doing a standard ERC-20 transfer, what happens is, the contract subtracts the amount from sender's balance and adds to the receiver's balance, right? Now, when we want to do this in a confidential manner, the amount and balances needs to be encrypted under corresponding keys, right, of the parties. Now, but now, how are we gonna, the contract needs to still perform this subtraction and addition, but the values are encrypted. So this is why we need to use some encryption scheme with homomorphic properties, and we are using an Elgamal encryption over elliptic curve. So the elliptic curve is baby jep here in this case. So it enables us to efficiently generate proofs over these ciphertexts. And also the structure of the elliptic curve Elgamal is pretty simple. The ciphertext is essentially 2 elliptic curve points. So homomorphic addition now corresponds to just 2-point additions on the contract. So the problem with Elgamal is that when you encrypt something using Elgamal, you don't encrypt the message directly. You first map it to some point on the elliptic curve, which makes it infeasible to decrypt, like inverse map the message back from that point if the message is too large, right? If this was easy, then we wouldn't have the public key cryptography over elliptic curves. So we need to solve ECDLP in reasonable time. So in order to prevent this, we basically added a new type of a new ciphertext. So when Alice is making a transfer to Bob, it encrypts the amount using Alice encrypts the amount using Bob's public key, using Elgamal. But now, along with that, it also encrypts using some symmetric encryption scheme. Essentially, this is what we call as PCT, Poseidon. These are Poseidon ciphertexts. Poseidon is, you probably already know, but it's a hash function. But when you use it in sponge construction, you can also get this very efficient symmetric encryption scheme. And we use this ciphertext as a helper ciphertext. And these accumulate on Bob's basically balance. So you have one homomorphic balance and one non-homomorphic array of transaction values that are encrypted. So instead of now you decrypting the Elgamal and trying to solve elliptic or discrete logarithm problem, you just decrypt all these Poseidon ciphertexts in linear time, and then sum up all the values, and then use this value as basically as a commitment for Elgamal, and you show that the Elgamal encryption, what it decrypts to, so you can generate proofs. Now there's a problem with that as well, because if Bob is receiving a lot of transactions, his array of these values will grow pretty quickly. So when Bob makes another transfer to someone else, contract prunes these entries, this array, and just puts a new single PCT that encrypts the most recent balance of Bob. So the efficiency, that's basically the design decisions that we made here. So we use Growth 16, so it's very easy to verify proofs on EVM. And the proofs just carry very minimal data as much as possible. It doesn't use FHE-like schemes. It just uses the very lightweight existing pre-quantum, I will say, cryptographic primitives, which are very again efficient on EVM. I will talk about the front-running problem, and the result is around 1 million gas right now on Avalanche C chain, which is like a 3 cents. Like a 5 maybe Uniswap swaps. So it's pretty efficient. So the front-running issue. So when we mean front-running here, again, this is not the front-running you have on DeFi, but you can maybe realize this from the previous example. So you have the ERC-20-like contract, but everything is now encrypted. The problem is now when I'm proving, so let's say we have Alice and Bob actually. Alice wants to make a transfer to Bob, but Bob, when Alice is generating her proof, right, like she basically says, okay, I know this, I have the ciphertext on chain and I can decrypt it and it results in this value, blah, blah, blah. But when you're doing that, the Alice's ciphertext, the balance ciphertext, might change on the contract, right? Someone else can make a transfer to Alice and change her ciphertext, which will invalidate her proof because the contract doesn't know that ciphertext, the new one. So Now, to prevent this, basically, we have something called balance list. This is like a temporary array, and when Alice is basically receiving transfers from other people, the hash of her balances accumulate over this array. So instead of contract checking, when Alice is making transfer to someone else, instead of contract checking, if the value being proven, the ciphertext being proven in this proof is the same as the most recent balance of Alice, it just checks whether if it's in the array. So it's like essentially, like in Zcash, you have the Merkle tree constructions, and you need to generate proofs, and those proofs may correspond to old root. So you need to store some past root history. This is very similar to that. The idea is, so what we realized here is that when the Alice is making a transfer, the contract is already aware of her that the Alice's balance cannot be less than the amount that is proven. She's proven right now. So when Alice performs another transfer to someone else, the contract clears this temporary list and places the most recent balance hash to the array, and this continues as it is. So previously there were like rollover functions, maybe from Zither and other constructions. This is much more simple, and it incurs very minimal gas. So the auditing is we have native auditability in eERC, and this is achieved by the same method that we use, I mentioned, for using Poseidon ciphertext. So we have an auditor key, public key, that is set on the contract, and zero-knowledge proofs enforce users to encrypt their amounts, also using this key. And these ciphertext will be emitted from the contract for each transfer or private mint deposit, that anything that needs to be audited, and they will live in events, and when the auditor, who has the corresponding auditor private key, requires like a decryption request from some regulatory body, they can just decrypt all this data and generate a kind of like a report and provide them to the regulators. And yeah, that's it. So the encrypted metadata, this is kind of simple. It again uses the Poseidon ciphertext because it's already used in protocol and it's pretty efficient. You can see from the right-hand side there is like an example usage from the code from our SDK. You just need to encrypt your message using the public key of the receiver, and then it will be part of the transfer. And this is kind of designed to enable, ISO, payment messages schemes, and essentially any JSON-like format. The eERC is actually already being deployed in Avalanche C-chain and used. The TVL, I'm saying TVL, but it's not the volume really because it's encrypted, has been surpassed $1 million. So the reason why we can see this value is because they use the converter mode. So we can just sum up all the deposited values, and that's around $1 million. You can check out their website. And all of our source code is available through GitHub, and thank you.
Thank you very, very much.
Do we have time for questions?
We can have a question because you finished quite quickly.
Okay.
Do we have any questions?
Yeah. We do have a question here, yeah?
Yes.
Yeah, I'll repeat your question afterwards.
Yeah, so doing some encrypted ERC, so what's the extra cost in terms of maybe chain, chain or validators or other means? What's the extra cost?
Just to repeat the question for the mic, but what's the extra cost of the encrypted protocol that you'll be using?
Mm-hmm. So it's very efficient, again, because if we can deploy this as a contract and it costs of $1 million gas, this kind of shows the efficiency of it. It doesn't incur any extra modifications on the VM itself or the validators. But in the user side, the users now need to generate proofs before sending their making any operation over eERC. We are using SmartJS with Circom here as well. You can check the code. And the circuits are pretty lightweight, so it takes like around 1 second to generate a proof from your browser. So I will say it doesn't incur any significant costs.
Okay, thank you. We'll save future questions for the break and lunch. So let's give one more round of applause.